Hello, my name is Pozo. I'm assistant professor at Skoltech. Today I'm going to present you my joint work with my colleagues Alexandre Velloso and Alexandre Street from Catholic University of Rio de Janeiro. There are a few key aspects for long-term planning in power system. One is it is a very complex system itself, but it still is interacting with other complex systems. There are uncertainties related with the long terms and versus short term, and we should make a distinction between both of them. For instance, wind capacity in a particular location can be considered as a long-term uncertainty, while wind production and this particular location can be considered as a short-term uncertainty. The way that power system can be understood can be evolved in future, can be seen very different from different experts. So there are two ways of looking at the future. So one will be like try to predict and try to find the best forecast of some particular parameters that will go into some planning models. And this is try to somehow find the most probable values for parameters, could be in some deterministic way or probabilistic way. But the other way is exploring the future. And this is what is called a scenario analysis. And this is what is typically done in industry and governments. So how we can combine both of these worlds together in some mathematical model, this is what we have developing here. There are several ways for modeling decision making and uncertainty. The classical one is the two-stage stochastic optimization. So we have to decide today what is the optimal decision of X that belongs to this calligraphic X. And there are some future operation of tomorrow, and we can compute some expected value that will depend, of course, of the decision X that we make today. Typically, in the two-stage stochastic optimization, P, the probability distribution is fully known. There are alternatives when the probability distribution is not known, what is called adaptive robust optimization. And the structure of this decision-making problem is the same. So we decide X in the first stage, and then in the final stage, we decide Y. But we consider that scenarios will be selected in such a way that maximize the worst case cost. There are another approach which is called distributionally robust optimization. In distributionally robust optimization, we still minimize the first stage investment cost, while we minimize also the expected operational cost, the second stage. However, P is not fully known, and we know some partial information of P. P, the probability distribution, it's supposed to belong to some calligraphic P, which is called ambiguity set. There are many different ways of defining an ambiguity set. It can be based on a family of known distributions. It can be based on moment information like means, covariance, etc. Or it can be based on a statistical distance. How looks like the structure of our transmission expansion planning problem formulation? Again, we minimize the investment costs and somehow the operational costs. In the first stage, we must decide what are the X, which is representing the new update of the grids. In the last stage, we have some expected operational costs. G is representing the operational cost that depends on the updates of the grid X. The short-term uncertainty, C, and omega is representing the long-term uncertainty. We must select what is the worst case probability distribution P that belongs to ambiguity set calligraphic D. Because we may have different long-term scenarios, we have this raw parameter that ponderates amongst all these scenarios. Well, the structure of this problem is a min-max-min problem, which is not straightforward to solve. So how we can solve this problem? So we present here an exact and tractable decomposition algorithm. So let's take the last part, the moment problem, this HDR. First part is the objective function, is expected cost. Then the sum of all the probability atoms have to be equal to 1. And the expected value of this uncertainty parameter C is between two values. So we dualize this. We have infinite number of constraints. Well, we can sample. So this is an approximation. The second approach is just, well, let's observe like this J is convex in C. By doing so, we can actually prove that this problem, which is infinite dimensional, but it's a linear programming problem. Solution of this problem will be always in the vertexes of the support set of the uncertainty parameter Kc. So it is possible to reformulate into a mixed integral linear programming problem without any approximation. However, this formulation can be computational challenging when this parameter Kc increases in size. For instance, when we have one dimension of the uncertainty parameter, the support set have two vertices. When we have two, we have four vertices. But when we have 24, there are millions of vertices. But once again, this is a LP problem, linear programming problem. And we know from linear programming problems that solutions are always formed by a simplex. In this particular case also, we can prove that we need only a simplex of the vertices of the parameter Kc. So for 24 hours, we will need only 25 vertices of the support set to have an exact reformulation of this problem. So we base our methodology in column and constraint generation. So in 2013, Chen and Chow proposed a column and constraint generation algorithm for adaptive robust optimization. In this, they propose a master problem, which is a small version of the original problem. From this master problem, it's possible to derive a lower bound. There is an oracle to find what will be the scenario that makes the maximum damage for this master problem. This can actually provide an upper bound of the original problem. We can add additional scenarios to the master problem. So this can be iterated until convergence. However, the Chen and Zhao algorithm cannot provide tight cut for our distributionally robust optimization approach. In their case, they need only one scenario to have a tight cut. In our case, it's not possible. So we propose a different oracle, and also we propose some decomposition technique, which is not explained in this video. Let's assume we have two long-term scenarios. They are coming from experts. They decided, like in future, we may have a scenario they call blue, which represents a high economic development. This is full of electric vehicles and full of electrification. They also envision another scenario, what they call green scenario. And in this scenario, there is plenty of distributed energy resources. So in the scenario blue, the projection of along the day of the daily demand is how you see here on the noon. You will see like there is a peak representing the users coming home and connecting the electric vehicles and using electricity. However, in the green scenario, the pattern of the net demand, this is system net demand, is inverted, because during the day they have enough PV production that they actually don't need energy from the grid. We test our methodology against adaptive robust optimization and deterministic case. The result of in-sample optimization give us for distribution robust optimization, we need to build 8 new lines. In the adaptive robust optimization, we also need to invest 8 new lines with a different investment cost, means like those are different lines. In the deterministic case, there is not investment. Well, the most important thing is just to look at the auto-sample analysis. So we have generated 10,000 samples. 5,000 of them, they are representing the simulated day for green and 5,000 blue. If we assume the net demand follows a normal distribution with low variance, we can test what is the performance of each of those methods. So for distribution robust optimization and adaptive robust optimization, they have a very similar reliability index, while distribution robust optimization have lower cost than adaptive robust optimization. But deterministic case, as expected, have a very bad reliability index. The main takeaways of this talk are the next. Distribution robust optimization can be a natural framework for long-term decisions. We propose and enhance the column and constraint generation technique for solving distribution robust optimization. that can provide a sub-deterministic formulation. We can provide bounds at any moment of these iterative algorithms, and it is relative. Thank you for your attention. If you have any question, I'm happy to answer by mail, and you have more information in this website.